had a good break. So today we're going to talk about the materials in chapter 9 and 10 on multiple regression, looking at different models, different situations, comparing models. There's no class on Friday. I'm over at University of Vermont, but there is the Pi Mu Epsilon lecture, induction ceremony. Hope you can go to that. Things you can be working on. Besides looking at the chapters 9 and 10, the next two chapters, 11 and 12, cover different topics in multiple regression. So we'll be looking at those next week. So if you wanted to look ahead to those things, you could look through the chapters, see some of the highlights that are there, or read them in more detail. A homework 6 will be posted that would be due next Friday. So it will be something that would kind of blend over some of these multiple regression topics, looking at using multiple variables in different contexts. Probably a couple problems, at least one to look at groups, another one to look at quadratic or interactions type of thing. So I get some little experience with that. There is this first project that's due in a couple weeks. I did try to investigate the NORC data about elections, and I did find a nice graph that was kind of interesting, but doesn't look like the data is available. That was in 2000, 2002. Their website called Retrieving Things from That, the Wayback Machine. So it's like old history to them. So I don't have those particular data that I had. So we need to find other things. Maybe some of you have already identified data that you're interested in. I have a couple other ideas, and so maybe I'll write up something about that, about possibilities. But that elections data does not seem to be possible. So anyway, the project's there. There's still a couple weeks to do it. If you were going to try and use one of your own data sets or something that's of interest to you, or think about topics you might like to do, maybe use some of the time that we're not meeting in class or over those days to think about that. Also, office hours are shifted, right? That instead of being Wednesday, Friday, something like that, with homeworks due on Wednesday, the homeworks are due on Friday, so my office hours would be this Monday, Wednesday, Thursday during the times similar as before, right? It's more concentrated just before the homework. So. But anyway, any questions about things? So we're kind of this pause and continue into multiple regression topics. And so today, primarily, we're going to look at some data examples of different things. This book has a lot of different data sets that cover different examples from different areas. It's really quite a lot to put together. And so let's see where they are when I started. Right. And so on this handout, these are some of the data sets that are in these chapters 9 and 10. There's the 4 case studies, and these are a couple things from some problems, right? Experiment, it's observational study on brain size. There's something on the pace of life in different cities and heart disease. In chapter 10, then there's something on the motions of falling bodies, very physical sciences application. And this other one about echolocation in bats and their energy. So just the ideas of measuring these things is pretty interesting. And then the problem with crab claws comes back. So in looking at these things in multiple regression, when you have multiple variables, we often will look at the scatter plots to see if it looks linear. But we could look at correlation or R squared to see if you're adding variables, is the ability to predict getting much better. Right. R squared is near 1 or 100% are very desirable, but in many applications you just can't achieve that because human behavior or things that are not physical science often are less. Yeah. So, right. We also do inference for coefficients in multiple regression. We do confidence intervals for a coefficient and testing for a coefficient, but we want to think a little bit about what that means because it's not quite the same as testing just when you're doing relationships with one predictor. That's very clear. Is there a significant relationship expressed through one coefficient with one predictor in there? But once you put in other ones, it kind of changes the flavor of the interpretation a little bit. We'll look at usefulness of regression plots. And then there's, in these things, using multiple groups or quadratic terms. So we'll look at it. We won't get to look at all of these today. That'd be too crazy rushed. But that's kind of just kind of an outline of what's there. These are the different names of variables that are involved in these. The first one I wanted to look at is this case study from chapter 10 on motions of falling bodies. Right? So this one was data like Galileo had, looking at a relationship. So let's attach that. And then plot. There's two variables, height and then distance. You throw something off force, right? How far is it going to go? And the higher it is, the farther it can go out, right? And this is the plot. Right? A very nice curve there, right? There's be very high correlation right, between these two things. And a linear model fit to this, what would that look like? So linear of distance versus height. And summarizing that model and putting the plot in there, that's what the plot looks like. Right? So it comes really close to the points, generally follows the strong upward, but there's a pretty apparent deviation from this, right? The quadratic nature of the motion is kind of showing up there in a curve. Now, if you have there's a linear regression output, all of it there, there's the estimated coefficients, there's standard errors, t-values, and hypothesis tests. So if we look at that, the test that we can do based on that, so this is the example 10 or 1, or the case study, not the exercise, the case study, right? In this first one, right, if we want to test the hypothesis, is the slope equal to 0 versus not? Right. A t-statistic from that regression, like I said, I don't have it actually written down there. The estimate is 0.33 with a standard error. The t-value is 7.93. Right? There's only 5 degrees of freedom because there's only 1, 2, 3, 4, 5, 6, 7 points, and we're fitting 2 things. So it's, but still the p-value is very, very small. So 7.93, and degrees of freedom are only 5 for doing that test, and the p-value is very small. If I had to write this in a paper, I'd probably write less than 0.001 instead of that actual small number, right? And so there is a definite positive linear relationship that's there. You can use the phrase statistically significant relationship as well. Right? But we obviously see something a little bit off, the quadratic, right? We see it just in the scatter plot, right? But if you also look at a residual plot, you can see some other things. So let's see, what can I close so that I can keep this one? Here, the pop under. No, I'm going to go on to one page. Right. So it's significant. The R squared is 0.93. So even though that the R squared is extremely high, right, there still seems to be a little problem with the model. If you do a residual plot the residuals versus the fitted values, you get that picture. So the residual plots make the curvature really pop out, even more so than on the other plots. Right? So we might want to put a quadratic. Putting a quadratic in R, it has a certain model language there, a little syntax for getting it to work. Right? Yeah.
Just a question on residuals. Like in terms of determining whether or not it's a high residual standard error, is the best way to determine that just by looking at the plot, or is there like a general, like usually numeric for each degree of freedom when it's considered high?
Well, it's going to be the residual standard errors. Like in this case, it's 33.68. So, some of these are -50, -40, 20s. So that kind of, it ends up being 33.68 in this example. So it has units. It has the Y vertical units. So it's going to depend on the context, right? If the measurements are in millimeters, then the residual standard error is going to be in millimeters. But if it's in miles, it's going to be different. And so,
so the actual numeric isn't as important. The plot seems to be a better.
so in terms of the regression assumptions,
Yeah.
right, then the plot would show you a little bit more.
Okay.
Right? This R squared value says something about the goodness of the fit, right? So if these were further from the line, more noisy, less precise measurement equipment and all that, R squared 0.8, 0.7 would not be as good of a fit, not as linear, right? As we add the quadratic, we'll see a change in both R squared and the residual standard error. If we can come closer to these points by having a quadratic, right, then we're going to get smaller errors, and those things are going to go down. So that's exactly the comparison, numerical comparison you can make between models for a given set of Y values. Yeah. So that's good. So if you try to put this quadratic in by, well, I'll just square the height. The model doesn't work as you would hope. It just has height in there. It just says height and then height again or something. So that's not the way to do it. If you put this little I here, it's kind of a little wrapper on there that says, consider this as a whole new variable. Right? This is, you could square height, attach it to the data set, and then put in both variable names and get it there. But, that means you have to add, you have to square all the variables and save all that. And it doesn't make much difference in this small data set, but if you put 500,000 observations, you don't necessarily want to square all the variables and save all that. So this one will make it square, right? But it drops the linear term. So that's getting closer. Instead, if you do height plus the square of it like that, that will get us both of height and its square in there. Right? So all this, that little bit here is just there's a little R syntax to get squares into the model. This has both. So the regression equation that this says is 199.9 as the intercept plus 0.0, let's see, 0.1. So just I have a 0 here. I don't need 0.708, right? Just one decimal place times height minus, and now there's 1, 2, 3, and then the fourth decimal place is 3, 4, 3, 7 times height squared. Right? Height goes 200 to 1,000, so you square that. That could go up to 1,000,000, but it has to go back to the scale of distance, so that's why you get such a small coefficient there. Right? And it's negative, right, because the curve is going down, so our quadratic equation is like that. Right? Now, this one has an R squared of 0.99, so we've gone up from 0.926 up to 0.99. That's improved. And this residual standard error has gone from about 32 down to about 13. But there's still some error. This is not a perfect relationship. There's measurement variability in there a little bit. You can get a plot of on there through a couple ways. If you plot the height versus the fitted values, the predicted values on the quadratic, it will take into account both those variables in the model. And if you make it, this is a type of L, so it makes it a line instead of individual points, and make it red, there's the quadratic line. Right? It's not exactly quadratic because it's kind of going point to point to point to point in there. There's also a curve function in R, so you can do a little bit more programming to make it smooth. If the x data here happen to be sorted, right? So it's the smallest one connected to this one, and they kind of plot in this order, and they get connected in that order. If they hadn't been in order, and you did that plot, it would just kind of zoom around to however the points were listed in your data set. You can order things by saving the ordering of height, right? Height with that little O in there puts the heights in order, and you apply the same ordering to the fitted values, and that would make this line in there if your X data weren't originally sorted. So some of the R commands, it depends on how the data is setting there. Other programs besides R, like SAS or SPSS, seem to have bigger issues with sorting and keeping the data in a certain thing. So R is pretty good, but you do have to sort it now and then. But anyway, that's the new fit. This one is much better, right? And usually this, when it's the height and the square is in there, we can test whether there's a quadratic component to this. We can test the hypothesis. Now is the small again. So height is x1, height squared is our x2, and so we can test whether the quadratic coefficient is 0 versus not. Right. The t-value for testing that is on the line of the output. For this one, that t-value is negative 5.15. Now we're just down to 4 degrees of freedom, because it's such a small data set. Right? So 5.15, negative 5.15. The degrees of freedom are only 4, but it's still, the p-value is very small. Right? And so the coefficient on the quadratic term is statistically significantly different from 0. From 0. At the alpha 0.05 significance level. Right. So you can make kind of a long statement to try to express that. Other people might just say that the quadratic term is statistically significant. Or just say it's significant, but it's non-zero. Right in there. You can get a situation where the quadratic term is significantly non-zero, but given that the quadratic in there, the linear doesn't show up. Right? If in fact the curve we had would kind of go mostly like this, the equation might be something like beta 2 x squared. Right? The actual model might be something like that. Like it might just be actually a quadratic term, or maybe you'd have a beta 0, an intercept in there, and there's not actually another linear component that actually determines that curve. Typically, we fit models in a hierarchical fashion, meaning that if x squared's in there, we generally want x to be in there too. That helps with the fit and doesn't impose any strange thing like we're trying to make it quadratic when it's not quite quadratic. So usually we fit models in a hierarchical manner. Right? So that we would typically keep the lower order terms in there. Because it just gives it a little more flexibility and avoids a situation where you're forcing it into that perfect quadratic relationship when it's not quite that. I don't know, it's generally the way that things are done, and it makes a little more sense. To me, it's easier to build up, keeping everything that was before. It also makes the number of possible models and ways you could do things really complex if you're allowed to go other ways. So, sometimes when fitting these quadratics, or you could have a cubic or higher, sometimes there's a very strong correlation between a variable and its square, right? So if both the variables are very large, if x height, if this had been something else like distance and had been very large, in the thousands or something like that, that and its square can be really highly correlated. So there might be a quadratic relationship, but you can run into some numerical estimation or calculation issues in computing things if there's this super high correlation of the x's. We'll see more of this in chapters 11 and 12. And so, as an example, let's take this data set. We could see maybe we'd want to have a cubic relationship. Maybe that would help a little bit. Or maybe to the fourth power, right, in there. So if we fit the cubic, lo and behold, the cubic relationship is also statistically significant. Right? There, not only is that curve quadratic, but a cubic fit seems to be better, having the height squared, height cubed in there. R squared now is 0.999. I mean, that's very little error. The residual standard error goes down to 4, right? So there's very little deviation from the pattern there. If you put the fourth one in, though, which that next code does, what happens? The fourth is not significant. Now the third is not significant either, right? There is, you're using up almost all the degrees of freedom by fitting almost as many coefficients as data points, so that starts to get to be a limitation. But this is not an atypical pattern. The height squared, height cubed, height to the fourth, some of those are pretty highly correlated with one another. So putting in more variables that are about the same numerical values, or kind of linear transformation almost, of the other ones, makes the calculation a little numerically unstable. And so if you do the correlation of all these different things, the correlation of some of these, so here's the height, it's square, it's cube, it's quartic to the fourth power. The cube and the quartic are nearly perfectly correlated. They're not exactly the same value, but because these values x's are pretty large, they're pretty close approximations to each other. And the quartic is pretty highly correlated with the square, and so on. The height and its square itself are pretty highly correlated, but you really get it big when you get the quartic in there. Right? So one strategy that if you ever encounter this in fitting quadratic and things is to take out the mean from some of the variables. Right? So if you take out, kind of center the mean, right? Think what would happen then, the height centered, some of those are negative and some are positive. So the square is going to look a lot different than the linear. Right? And the cubic, some are going up and some are going down. So it reduces the correlations quite a lot. So if I do that and then look at the correlations between the centered ones and the original are much less. So it avoids this numerical problem that you would have with really highly correlated variables. So now, if we put all four in there, well, the last one still is not significant, but maybe it's not really needed. But the third one still is, right? The third one by itself was significant, and so we've not lost that as an apparent significant predictor through the centering. Right? So I think when we just did the third and fourth without centering height, this one also became not significant, not apparently relevant to the prediction. because of numerical issues. I think the fourth really is not needed. We don't, it's not really helpful in this context. Right? But anyway, so that's really that example of kind of diagnosing. Maybe you need quadratics. It shows up in the scatter plot. It really showed up in the residual plot. And that's how you can put them in there. A little syntax to get it to work, but then it's fine. So that's one of the examples of something you can do with multiple regression. But any questions about this one? Or? There's an economic data set called Longley's economic regression data. And in this one, there's probably there's an issue with this data set of trying to predict GMP based on a bunch of variables. The x's are very highly correlated with each other, and so it's called collinear. So again, this one is another example where you put in a bunch of variables, a bunch of things that look significant individually, when they're combined, because they're all very highly correlated, they're all growing together over time, end up being not significant. So there's an issue of something. We'll probably come back to that as an example, but the second one I want to look at is this one with bats. Right? So here's a plot of the data. Right? So bats move by echolocation, right, or travel that way based on the mass of the bat. They use a certain amount of energy. I'm not sure how this was measurement details, but anyway, you get a relationship that looks pretty strong in this, right? So if we can do a model to predict, and we get an R squared of 0.86. The coefficient for mass as a predictor is highly significant there. It's kind of spreading out a little bit, so you might think about that, but it's not too bad. But there are different types of flying animals in this. There's some echolocating bats. There are non-echolocating bats. Right? And then they had some non-echolocating birds, which must be about the same size as the bats. Right? So it's not really a big data set, right? So how can we use these different groups in this analysis? One thing we want to do is see where they are. I'm going to define a new variable called group and just use 3 letters in here. So I'm going to use E is going to be for the echolocating bats, right? And N is would be the non-echolocating bats. And then I, because there's an I in birds, is going to indicate birds, right? So I'm going to get these letters here. So initially I put 20, there were 20 data points, so I put E for all of them. And then I replaced them where they were N and I. There's probably fancier commands for doing that. But anyway, that works for me in most cases. So then I plotted those things. So here's the plot of these different symbols. Here's the non-echolocating bats, the echolocating bats, and the birds, the eyes of the birds. B, I would, thought, could I use B, bats and birds? They're both B's, so I don't know. What do you think about this? I wanted to see a little bit more, so I did a color version of that thing and see how it lined. This is the plot with color. Right? So I had one professor in graduate school who was colorblind, so he hated color graphs. He said, you can't make all your graphs with color because not everybody can see it. And when you print it on a normal printer, you're not going to get color, so make sure people can understand it if they can't. But anyway, there's the N's, the non-echolocating, the birds, and then the E's. It's a pretty striking example of how limited these data are, right? Because there's only the 4 echolocating bats, and 3 of them are almost on the same spot, and there's others here, right? So it's really quite limited, right, what you can say. But there's these 3 groups. So there could be an interest in, is the relationship different in these groups. And one way to start looking at that is to put group in there as a variable. Now group, right, was the E, I, and N, so it's letters. So R is going to know that it's not numerical values. If I label the groups 1, 2, 3, R would try to use group 1, 2, 3 as numerical, which wouldn't make any sense, right? Because the 1, 2, 3 labels are really arbitrary. So if we run that and then do that summary of it, right, we get this output. You get estimates, standard errors, t-values, p-values. R squared goes up to 0.89, 88. What was it before? Before it was 0.86. It's only 8. It's not a really great big increase. Right, we've added 2 coefficients effectively to represent these 3 groups, but R squared hasn't gone up all that much. R squared adjusted is this other measure. R squared adjusted before was 0.85, but R squared adjusted now goes up to 0.856, so it's only the 3rd decimal place. So there's a little bit of gain with this R squared adjusted, but it's not very much. Right? What do these t-tests, right, show us here? Right? That if we did an individual t-tests for this, right, we can test, right, is the slope statistically significant? Is the slope on mass kind of a growth independent, are different, significantly different from 0? And this is still statistically significant from 0. Now the coefficient and the standard error and everything changes from the simple regression because these other 2 variables are in there. Right? So it's statistically significant accounting for a group difference. Right? So the statement about it is just a little bit different because the other variables are there. You could test based on this is group N. So what is this equation giving us? Here, the bats. So y hat for the bats is 1.42 plus 0.057 times mass plus the 4.6 I, so that's birds, plus 1.17 times N. So these are bats. They're the non-echolocating variety. They do not use echolocation to find their way around. So that's the equation. Right? So what's the prediction for an echolocating bat? Right? So there's the echolocating bats, there's the non-echolocating bats, and there's birds. So this equation really gives us 3 different lines. Right? For echolocating bats, it's not a bird, and it's not this one. So both of those are taken as zeros. Right? So this one gives you y hat equals 1.42 plus 0.057 times mass. But if you're a non-echolocating bat, right, then you get to add in 1.17. So you get the y hat equals the same thing here, plus 1.17. And if you're a bird, you get the basic equation plus 4.6. And so this changes the intercept, right? So what we're really getting here are 3 parallel lines going up with the same slope. The mass, the x variable, and energy. Right, that's the y variable up here. And so you get these 3 parallel lines. Right? And so if you have a value of mass, for those, your predictions are going to change by that constant amount. So that assumption of straight lines, parallel lines, is an assumption of the model. Might or might not be true. It's kind of hard to tell in this case because we have such small data. And then the hypothesis test right? We can test whether one of these coefficients is 0 or not, right? If you change the order or change the alphabetical lettering, that's going to change the coefficients, but they're going to have the same magnitude if you put things back in the scale of the different species, right? If it had made, so kind of, they would talk about the echolocating bat as being the default value, and then these others are changes from that. If you had changed it, and I'd done my color symbols or arbitrarily labeled them otherwise, you're still going to get this for one of for the bats, and this will still be, but it would be, you might have a different intercept over here, and then minus for the 6 other ones. It just happens that the echolocating bats seem to be the lowest in terms of energy. Right? That's what they do to get around, so they seem to make less energy, so require less energy. So we can test, is the coefficient for birds equal to 0 or not? So the estimate for the birds in this is the effective birds. The addition of birds is 4.6. Its t-value is 1.3. The degrees of freedom we use in the t-distribution, there were 20 birds, and then we've had the intercept, the mass slope, and 2 indicators. So we have 4, so it must be about 16. And the p-value that's reported in the table is 0.212. So this would say that we do not reject the null hypothesis. That the bird effect is not significantly different than the default. From 0, it's really 0 change to the intercept, to their intercept. So it's really testing, do you need an offset for birds or not? In this case, we don't think they do. Right? So if you just do one coefficient like this, you're left with kind of a funny situation, right? You'd be left with a situation where, what does that mean if it is 0? That y is beta 0 plus beta 1 times mass plus, beta 2 times the non-echolocating ones plus the errors. So you end up with one group being different from the other 2. That's possible. That's possible. That's okay. It could happen in situations, but it's a little bit funny to think about. You certainly could think about that there's one group that's different from the others. What's more typically done is to test, is there any group difference versus is there any group distance at all? And so for testing, is there any group difference, is what's called this nested F-test or analysis of variance. So model 1 had just the energy and mass. Right? And model 2 had the energy and the indicators for these several groups, the 2 indicators in this case. And so if you do a ANOVA comparing those two, it gives you this output. Right? And so this test has 2 degrees of freedom that it's using, and it's testing whether the 2 groups are significantly different simultaneously. So what's probably preferred over testing just a single group at a time is to test, in this case, is the intercept change for birds and the intercept changes for non-echolocating bats both equal to 0. And the alternative is that BI is not equal to 0 or B sub n is not equal to 0 or both of these things are not equal to 0. So this is a model where, I'll just write these values, is beta 0 plus beta 1 times mass And this model down here has, it could have a coefficient for the birds. It could have a coefficient for the non-echolocating bats. Or it could just have one of those. So to test this, it calculates an F statistic. And this sometimes is called extra sums of squares. Because we're going to take the sum of squares error under the first model minus the sum of squares error under the second model and divide by the change in number of parameters, which is 2 in this case. So sum of squares error under the small model is bigger. Right? You don't predict as well with fewer variables. Right? So this is the change in sum of squares. It's the change also in the regression sum of squares because everything's additive there. Right? So, and then you divide that by the better estimate of variance. So you have the mean square error under the second model. Okay? And then this thing is distributed as an F distribution under the null hypothesis that says that the smaller model is correct. This thing's an F statistic with 2, and then the degrees of freedom for the second model, and its mean square error, which in this case would be n minus 4 for the second model because it had 4 coefficients. And so this one will reject if the F statistic is big. Right? And if it rejects, that means that there is some group effect. In this case, right, so that's the extra sum of squares. It's very flexible for comparing groups of variables. Put it down here. So in terms of our output, there were 20 birds or bats, right? So we had 2 coefficients. It was 18 degrees of freedom. When we had the 4 coefficients at 16 degrees of freedom. This is the change in residual sum of squares, right? That change. The difference in sum of squares was 78. Degrees of freedom are 2. And so what it's doing the sum of squares over 2 divided by the residual sum of squares over 16. So let's write that out, and that would be our F statistic of 1.4. So it doesn't give you quite everything spelled out there completely. So in this case, our F statistic, taking off that table, so the change in sum of squares is 78.827. And you divide that by 2, because that's a change in, if you had 6 groups and you needed 5 indicators, you'd have 5 there. Right? We had 3 groups, so we need 2 indicators. And then we do the mean square for the small group, for the bigger model, 450.03 divided by 16. And that ends up being 1.4013. And you compare that to an F distribution with 2 and 16 degrees of freedom, and the p-value, the probability that you're greater than or equal to that, is 0.27, right? For this one. So we don't reject. There does not seem to be a difference in the energy-mass relationship. So this would suggest use y equals beta 0. So use model that's beta 1 times mass plus an error. And based on this small data set, we do not see a significantly better fit by adding the different groups. Possibly because we have such a small data set. Now the book suggests a log scale for doing this. Right? might. But these data, look pretty straight. But what if we do the log scale? The log scale actually looks a little bit straighter. It's kind of subtle, but it actually seems to work. Maybe there's a biological relationship. That energy and mass are multiplicatively related to each other. One's a fraction of the other somehow. And so taking the logs would straighten that out. It seems to work empirically. Right? If you update these two models for the log predictions, so this one, log energy is a function of log mass. There's a way to just add the groups in there. There's an update function. So this one says start with what you had from the mod 1, and then don't change y, don't change, keep all that other log mass in there. Whatever these have been here as predictors, keep those, but now add group effects. And because groups is the letters E, I, and N, it treats them as groups. Right? So it's going to add those in, and this is what we get as a prediction. These p-values are even less significant. And if you do the ANOVA, maybe I didn't run both of them. Updated summary of the mod 2, okay. And then this ANOVA, the p-value again is not significant. So on the log scale, there doesn't seem to be any evidence. What if, though, just hypothetically, just to see a significant effect, what if the non-echoloding back the ends had been higher, right? A little bit higher, just artificially. Just perhaps they require more energy for the amount of mass. Right? So I'm just going to copy over that energy variable, and for the group that's in, I'm going to add 25 on the original scale. Right? So the original scale had a bigger range. I want these to stick out. And I tried moving them up, and there happen to be some I's that are kind of high. So initially I tried 10 and then 15. But once you get up to 25 as a shift, here's the plot, right, on the log scale. Then the ends kind of stick out of the pattern. And if you refit the two models with the new energy, the summary then shows up like this. Right? With the ends pushed up here, it looks like they do need an extra boost to their intercept to fit them. Right? And so they're significant. If you run the ANOVA on the new data set, it has a significant result. Right? And so it means that one of these groups, at least, or both, right, need to be separated. And looking back at the regression output, it looks like just the non-echoloding bats. So the birds and the echoloding bats in this artificial change of things, right, are sticking out. Right? It's possible to, if you thought that really that this was one species that's different from the rest, you could just put an indicator for one group in there. It's a little smaller model, and that would help. But anyway, so you can get groups in there. And we're really kind of out of time. This other data set, heart and pace of life, was one of the exercises. There were some variables about how fast-paced things are, and amount of heart disease there are. How fast do the people walk? How fast do they talk? How fast the bank tellers do things? Is increased pace associated with more heart disease and stress? Probably through stress. So the reason I was going to look at this one is like, well, how do these start something? How would you pick a variable to begin with? But one way to look at it would be to plot all these things, but you could also look at the correlations. Right, and the correlation with heart, oh wait, we go to 1045. I always get confused between the two classes, so good. Enough time. So if we wanted to predict heart disease, we'd look at the correlations of the other variables with heart disease. Right? And it looks like the walking pace is more associated. So the more you're rushing around. Closely behind is the pace at which the bank tellers do things. Right? Talking, though, doesn't seem to have as much of a relationship. So if I would start, I'd also probably do this pairs command, which says pairwise plots. It's a little bit small to see, but if you want to predict heart rate, do any of these show kind of a relationship? And walking was the highest correlation. That's a correlation of 0.35. And then banking, 0.332. And then this one's more flat. So it's not a strong picture, but there's a little bit of a tilt in there. So I would start with walking. If you run that model and do the summary, you get an R squared of 0.12, which is the square of the correlation. Not very much, but it's human behavior, some imprecise measurement of human behavior, and then some measurement of aggregate heart disease, which has a lot of things that contribute to it. So it's not surprising that it's not quite as high. But walking is statistically significantly related. The test is that coefficient 0 or not, gives the p-value of 0.03. So it's significant. R squared is 0.12. The mean square error, root mean square error, or residual root is 4.96. And so at this point, we have one predictor. Should we use another one? We can look at residual plots and other correlations and other models. So you can plot the residuals from the walking relationship versus your other x's. So we haven't used bank speed. So there's a relationship there. Does there appear to be a linear relationship between the residuals, what's left over, and this? Not too strong. I mean, these two people low here, so maybe you can imagine, squint a little bit, right? Something like that. Versus talking, no, I don't see anything there. You can look at the correlation between these things. And so I wanted to show up as a little name, so you can name things in this. The correlation between banking and talking and the residuals. And this last line here. And there is some correlation between residuals and banking. That previous plot, right, does get a correlation of 0.3. There's a little bit of correlation. These two being down here mean that you could put something in here that's a little bit better than flat. The flat line kind of goes away from those. So you can tilt it a little bit and get it. There's not much of a correlation with talking. Right? That just the 0 flat line looks pretty much appropriate for that. So you might try adding these other ones. If you just add banking, it's almost significant in there. Right? It's just kind of on the verge of being statistically significant. R squared goes from 0.12 up to 0.20, so there's a little bit improvement there. The residual standard errors got smaller because your predictions are closer. And so it's almost statistically significant, right? This was 36 cities with these measurements. So often in social sciences, getting that little bit extra prediction is really good. So if you had to publish a paper, I'd probably try to publish both models. Right? Say this one was significant, this one was almost significant, and improves things. Kind of suggests that if you did more studies, that both of these things. Right. So there's walking, banking, kind of two different dimensions of life, but not completely separate, but both of them together do a little bit better. If you put talking in, it's not statistically significant in there. Now, just because talking is not significant here, doesn't mean that the speed of talking is unrelated to heart disease. But given that walking and banking are in the model, talking is not a significant predictor. So, what do these models mean? Is there a relationship to reality? And sometimes we fit models just to do good predictions. And we're not trying to capture something like Galileo's movement of planets or a physical relationship. We're just kind of taking the data as we have and trying to do predictions that work out well. The walking and banking as two predictors, does that really correspond to some physical dynamic that causes heart disease or something? No, it's just more emblematic about stress and pace maybe there's some explanation related to that, but does it show, is there a clear biological channel that you can show that it's true? I know, I doubt it, right? You might measure some different brain chemicals and things that cause hardening of arteries over time and in a very complicated way and get something out of it. But more it's just taking advantage of what we have and trying to do a prediction. But this says that talking, when you have walk and bank as predictors, does not add anything. So it's not related. And in fact, if you just do a regression of, if we do a summary of little model of art versus talking, right? Well, that one, I guess, is not significant. There does, maybe that's not talking versus art. The speed of talking just doesn't seem to be, but that's not always the case. You can have different variables that are significant. So like this one with just the two, right? Banking is not quite significant, but if you do a regression with just banking, right? Oh, it's not quite significant either, but it's closer, right? It's getting closer. So, but you can have things that are significant just by themselves, but once you put in something else that's kind of showing some of the same pattern, the algorithm just has to minimize that sum of squared error in some way, and it can make one variable less important and another one be the significant one. Just because there's a little tilt in one gets a little bit better predictive value. So anyway, so in getting started with these things in multiple regression, look at pairwise plots, look at correlations. Does anything need a log scale? Are there any real extremes are there groups? Then start with some things that look like your best variable. Highest R squared, highest correlation, best correlation with a variable. Try to add the next one, maybe look at residual plots, maybe look at groups. And there's kind of an art of, people could say art, but it's just kind of a process you have to go through with looking at things. You can't just jump to a model and say this is going to be my model and this is the way it is. Right, so you can do some interesting things. So no class on Friday. We'll come back with Monday and look at some more kind of formal diagnostic things. We're checking assumptions and concerns in regression. And by then, homework should be posted for them.
So the homework will post on Monday, you think?
I'm probably tomorrow. I'll try to get posted together with the week to do it. So right, when you put height square, it just thinks about height and height again. So just
I was thinking about it because I was remembering the players in your team. Like, how do you get
to
to
make
make
things distinct there.
You started Michelle and Lindsay.
Yeah.
David Johnson.
Goff did well. Like
Or
kicker
this one could-
was.
You started Goff?
He said it right.
And so R, like those that go in, you want height squared, height cubed together. And you put these little I things, it tells it to treat it like a new variable. It's just the syntax for R, doesn't that work out?
So we can also talk about like inequality, but I think it's generally, it's a whole lot of things you can do with this, so much to like.
The square?
Yeah.
Well, in this case, we wanted a square of height, or cubes, or to the fourth power. So this was getting height and height squared, so it's x squared, x cubed, x to the fourth, as you want those
We
things.
could look at equality positive. Yeah. Alright, then we should
Oh.
talk about.
Okay, good, thank you. Yes, you had a lot going on with the presentation too, so. Good, thank you. Mm-hmm.
Yeah, but I like that.
Well, let me look at the,
Maybe like know a little bit.
you know, know, like the textbook we use from the biostatistics, this is 140, had a chapter on multiple regression.
Alright, see you
We
later.
didn't do the multiple regression chapter in this case, it's 140. Not really in very much detail. But there'd be some data sets in that. I could look through that textbook and, I have those data sets, so that would be one possibility. In that class, we also looked at an online book. There's an online supplement. We looked at a couple times, but by McDonald. So that online supplement had some R data sets as well. So that would be another possibility. But let's check on that.